Hello, in this video we're going to be learning about charge and current as functions of time in a charging capacitor circuit. So, I've already drawn the circuit here. We have a battery, a capacitor, and a resistor. From what we know about circuits, we know that the current is going to flow through from the positive end of the battery to the capacitor. We're going to have positive charge build up on this side of the capacitor and negative charge build up on this side of the capacitor, and the current will flow through. And this will continue until the potential difference across C, or across the capacitor, is equal to the potential difference across the battery. So, what we want to do is we want to be able to write charge and current as a function of time for this particular circuit here. And the first thing we need to do to achieve that is we need to quantify the behavior of the circuit with time. And to do that, we can invoke the loop rule. The loop rule states that the potential difference across the battery is going to be equal to the potential difference across the rest of the circuit. And so, how could we write this for this particular circuit? We know the potential difference across the battery is the EMF. And when we say something is equal to each other, that means that if we subtract them, it will, their subtraction will be equal to 0. So we can say minus, what is the potential difference of this capacitor? In this case, we need to say the change in V of the capacitor. And then also minus, what's the potential difference across the resistor? Well, we know that the potential difference is equal to current times R, so we can just write IR. And that's all going to be equal to 0. Now how would we find this value? Well, we know that voltage is charge over capacitance. So we can write again. And another thing we know about current is that current is equal to, what is current? How do we define current? We define current as the flow of charge over time. So dq over dt. Let's see that a little bit better. So let's write this again. We know that the potential difference across the capacitor is Q over C, and I is equal to the change in, is equal to dq over dt. So we can insert those in, and that's all equal to 0. So we have successfully quantified the behavior with time. But we can take this a little bit further, because right now this equation is confusing. We have dq and dt. We have two derivatives in this. And you can recognize this, actually, this entire equation, this is a differential. Diff-eq. So what we can do is we can solve the differential equation, and I'll take you through that process of solving the differential equation. So we can bring dq over dt to this side. Oh, I apologize. I left out the r here. This needs to be multiplied by r. I knew something looked wrong. So then we can divide both sides by r. And then we can combine these fractions. Now, what's the next step in a differential? We want to separate, oh, I'm sorry, you can't see that. We want to separate dq and dt. So let's bring dt over this side, and let's bring q over here, so it's with the q. Okay, and one final thing, just to make this a little bit easier in the future. First, I'm just going to switch the size of this equation, just so it's easier to read, and also I'm going to multiply everything by -1. So then we get negative dt over RC. And this is Q minus EMF C. So then, the next thing you do when taking a differential is to take the integral of either side. And what do we want these from? We want the integral to be going from where q is equal to 0 to q is equal to q, because it's just some arbitrary number right now. And the same thing on this side, we want it to be going from where t is equal to 0 to t is equal to t. I apologize for my marker, it might be a little bit hard to read. So we can integrate this side. We know that when we take the integral of 1 over q minus EMF C is going to be the natural log of the absolute value of EC, all from 0 to q, and that's going to equal, what's the integral of dt over RC? Well, RC are both constant values, so it's just going to be negative t over RC, and that's from 0 to t. And so how do we solve for a natural log? We can raise each side, or do e raised to each side of the equation. So then we get q minus EMF C over negative EC is equal to e to the negative t over RC. And then we can solve this side for q. And what we end up getting is q is equal to C EMF times 1 minus e to the negative t over RC. And that is how you find the charge as a function of time for a circuit with a capacitor and a resistor. And so we can see what this actually means. So let's draw a graph of this. Let's look at the... This is going to be for the equation that we just wrote. The equation we just wrote was Q is equal to C EMF 1 minus E to the negative T over RC. And this axis will be charge, and this axis will be time. And if we draw this, we'll find a line that looks like this that tapers off. And this is Q of t. And what the value that this is actually approaching is when Q is equal to C EMF. And so that's really interesting. You can see that as time passes, the charge will increase until it's approaching the capacitance times the EMF. And so that's what we know about charge as a function of time in this type of circuit.